today. There are the course evaluations out, so please, if you have the time, fill them out, and this will also help us to understand what to improve. There is the second homework that we will go over, but first, at least like the most basics from the first homework. So I think one of the questions was the weaknesses and the strengths of the two methods. So at least let's go over that together again. Can can maybe one tell me what they think are the strengths and weaknesses of DSHA? Yes, please. Okay. So having one governing scenario, you can say that maybe that makes it like a simpler calculation, right? And so it's more transparent as to uh, uh, yes. No, I agree with what you're saying. So in that sense, so PSHA you will say is more complete as like sort of, but in terms of like having something simpler that you can follow, maybe someone can argue DSHA. But again, I get your point. PSHA on its own is not that difficult. And so you mentioned that, and what was you said your one governing scenario, and then what was the second thing that you mentioned? Ah, the full distribution. Okay. So in DSHA we use one scenarios. So let's say let's argue that one of the strengths is sort of its simplicity. Any weaknesses that just selecting one scenario may bring? Yes, please. Y- Yes. So it doesn't account for that range, and so it kind of assumes that you need to know a priori what is the controlling scenario, right? And when we select that scenario, uh, do we take into account how often it happens or no? Implicitly, we do, because a large magnitude earthquake can happen anywhere, but it may be so rare that we consider it highly unlikely, but we are not explicitly accounting for that. So there is like some judgment as to a large enough scenario, but a large enough scenario that it's still relevant. Any other weakness that it may have? Mm, mm. When you select like when you say like I will run my deterministic analysis for a magnitude 7 at 30 kilometers away, uh, like you can always have a larger earthquake, but like so let's say you are in California. There may be the possibility that the entire San Andreas fault will rupture, create a magnitude 9, like a rupture that will start from Los Angeles and will go up to Eureka. Although this is sort of within quotes, the largest magnitude that can happen, you will not include it in your deterministic analysis. And that's because the probability of that or the return period of such an event is 1 over 10,000 years. So it's highly improbable. Is that making sense? And maybe that also gives us the sort of third weakness, which is I was a little confused why I think almost anyone or everyone said that like, is it really the worst case scenario that the deterministic analysis will provide? Why would that be the case? Correct. That's true. So we kind of we the way that typically you define that magnitude is like the characteristic magnitude, and there can be a larger one. But even if, let's say, we selected the largest earthquake, would that make deterministic conservative? Would that make deterministic give the conservative ground motion, or still there may be a case that it will be exceeded? Um, when we define the worst case scenario, do we talk about the size of the earthquake or do we talk about ground motion? I think we typically define it in terms of ground motion because it's the worst case for our structure, and our structure doesn't care about the size of the earthquake, it cares about the ground motion. So if we define it in terms of ground motion, then the magnitude alone, does it fully describe the amplitude of shaking, or no? We also have the different percentiles that define the probability of exceedance. And in the deterministic analysis, we typically use the median, we use the 84th percentile. So even in the 84th percentile, there's 16% that something larger may happen. And those, like, at least in the way that we formulated the problem, we assumed like a normal distribution that extends to infinity. So there is really no way of capping the problem. And that's a parenthesis, but like there may be some confusion because like even in the building code, the deterministic scenario is described as the maximum credible earthquake. So it's really important to take into account its maximum, but in terms of like within the credible events. And even that is only referring to the size of the event, not to the size of the ground motion. So if that's the strengths and the weaknesses of DSHA, what are the some strengths and weaknesses that we can think for PSHA? Yes. Yes. And when you say considers all the sources in terms of their probabilities, how do you find like the probability of them happening within a year, so the rate of those events? Some other strength or weakness that it may have? We have limited data and no, no, so we have limited data. So how do we describe the range in the possible models that we can have to reflect the lack of data? Yes, and when we talked about epistemic uncertainty and aleatory variability, where would you, like, what group would you use to describe this limited data? Like, would it be an epistemic uncertainty issue or an aleatory variability? Yes. Epistemic is like, what does epistemic means? Scientific? Yes, it's a synonym for scientific. It's like actually the Greek word for scientific. So it's like the scientific uncertainty. And we use scientific uncertainty to define the range of possible answers based on like the amount of information and data that we have. And so in areas where we don't have uh, a lot of knowledge, then we have broader epistemic uncertainty to reflect that, like in how we like. For example, you saw that we had the like in the magnitude recurrence models, we have the slope of the model that is the p-value. If you don't really have the data, you don't really know what it is. So you will say, okay, b can be 1, can be minus a, can be zero point 0.8, can be 1.2, and you will consider all possible scenarios. So you can include that, but then if you have large epistemic uncertainty and you run the calculation, but in the end you just report the mean hazard, we haven't really looked at that, but like in this homework we will see it most likely. But if you just report the mean hazard, then all of this uncertainty that you have propagated, you are losing it because you are like overly relying on sort of your average assumption. Um, And I think you already mentioned the other, like it accounts for how often the different earthquakes happen and what are all the possible earthquakes that we may feel, not simply what we consider a rare but still reasonable scenario. And so in that, where do we think we need like judgment is introduced is in setting up the problem within each of these frameworks, where do we need to add, like, to use judgment to define the different parts of the model? So yes, so in a PSHA is what scenarios you use to the epistemic uncertainty and how you weight them, right? Anywhere else? The selected percentile for PSHA or for DSHA? Excuse me? DSHA, yes. So how would you select the 50th or the 84th or anything else? What would be the equivalent decision for PSHA? How do like the PSHA gives us the hazard curve, and how do we get the design ground motion from that? We read it for a specific return period, right? So we say that like we want the ground motion that corresponds to the 500 return period. So the ground motion that is consistent with an annual hazard of exceedance of 1 over 500. Is this clear or not? Like if you have a hazard curve that looks like this, what is the x and what is the y axis? This is our hazard curve. You already did that, I think, for assignment 1, and I think for that, most of you did it correctly. The x-axis is some type of intensity measure, like most commonly spectral acceleration, but it can be duration or anything like that. So let's say spectral acceleration. What is our y-axis? Yes. Or otherwise we call it hazard simply. And what are its units? 1 over time. And typically, if we talk about annual rate of annual frequency of exceedance, is 1 over year. Right? This is why not Z. So, and we have like from decreasing to increasing value. So we have like, let's say that we want to design the ground, so our structure for a hazard level of like 500-year return period. So we'll go to the point that is 1/500, see where it intersects the hazard, and read the ground motion. And this is our design ground motion value. So whether we use 1/500 or whether we use 1/2500 or any other value, again, we need some judgment there. And the same way that based on the importance of the structure, we decided whether we will use the 50th or the 84th percentile or something else. The hazard level that we has to do with how important our structure is. So in DSHA, I think you already said it's the percentile and also the scenarios that we select, right? Because again, it's this large event, but also reasonable. And in PSHA is the weights that we assign for the epistemic uncertainty to properly represent it, and the hazard that we select for the design values. Maybe this is sort of the last as a recap. So this is kind of to reinforce the idea that DSHA is not more conservative. So whether PSHA or DSHA will give us, which of them will give us the largest value has to do with how we compare them. And what we have flexibility in selecting DSHA is the percentile, and what we have flexibility in selecting in PSHA is the return period. So if we say that we run, just make sure that or whatever return period we care about. And we get, like, from the deaggregation that we saw this week, I believe. Okay, so we have PSHA and the deaggregation. And so we have the controlling, the magnitude and the distance for the controlling scenario and the epsilon. And let's say this is, I don't know, 7, 10 kilometers away and an epsilon of 0.8. Okay. And now let's say that we run a deterministic. We run the SHA. We happen to select the same magnitude and distance. So we have a magnitude of 7 and a rupture of 10 kilometers. If we were to use the 50th percentile for the DSHA, will we get a smaller or a larger ground motion? Okay, so because we have the same scenario selected, so same magnitude, same distance, and same VS30, we have the same median and standard deviation for both cases. So the mean, like the mean that the ground motion model gives us, that is a function of M and R, is the same for both cases. So what would be how can we calculate the median ground motion will simply be the exponent of the mean that we get from the ground motion. the fact that we can get the mean and the standard deviation from a ground motion model as a function of magnitude, distance, VS30, and so on. Is this clear? Okay. So this follow in log space. Normal distribution. We talked about the median. How do we define the median? What percentile corresponds to the median? 50th. Meaning that half of our distribution is below the median, half of the distribution is above the median. What is the median for a normal distribution? The mean, right? Because it's a symmetric distribution. And since this is in log space, to convert it to linear units, we take the exponent, right? So PSA median is the exponent of mu. So if you were to run the SSA for the 50th percentile, then that is the value that it will go with. Can someone, the key here is the epsilon. So we have a positive epsilon deaggregated from PSA. So does this mean that the ground motion that goes with PSA is above or below the median? How did we define ground motion as a function of mean and epsilon?
I think that for the DSHA.
Epsilon is 0.5. If you were to guess again, another number, it should be 0, right? Why? Epsilon is, what distribution does epsilon follow? A particular normal, right? The standard normal distribution, which has a mean of 0 and a standard deviation of 1. So epsilon follows a normal distribution with a 0 mean and 1 standard deviation. And so you can assume standard deviation, you will go to standard normal distribution. And as you said correctly, the median ground motion corresponds to an epsilon of 0, because like if you were to apply this transformation again, you will say PSA for some epsilon is the exponent of mu plus sigma epsilon, right? So if the PSA gives from the indication we found that it corresponds to a larger value of epsilon, a positive epsilon, then this value, this design value, is larger than the PSA. Is this clear? If this is clear, who can tell me if the SHA is performed for the 84th percentile, whether it will be smaller or larger than PSHA? And to tell me that, you need to figure out like what is the epsilon that goes with the 84%. It's not 0.84, it's hmm? It's one. Oh, delete. Damn it. Really? Absolute probability. So the epsilon is like this will be the epsilon. So this is epsilon of -3, -2, -1, 0, 1, 2, and 3, right? So this knowing that epsilon of 0 corresponds to the 50th percentile, and if you start summing all of these areas until an epsilon of 1, you will get like it's like you have 84% of the distribution being less than that value. And then for an epsilon of 2 is the 96%, 98th percentile. So you have 98% of the distribution less than the value that corresponds to two standard deviations. Is this clear? So if you go back to this slide, for like, so this was done I think in 2000, but they simply went and performed a probabilistic and deterministic hazard analysis for a number of sites in California, and then so if you have for one site, if you have like the hazard curve that you get from your probabilistic seismic hazard, where let's say this is PGA, this is lambda, this is your hazard, and from your deterministic you have say um, deterministic being some value, I don't know, z star. You can find this value z star and then find what is the hazard that it is associated with. Um, so this is the distribution that we get. So in some cases, the return period is goes from the deterministic analysis to a very small hazard value. And that means that in those cases, the deterministic scenario was the conservative one, because it corresponds to a more area ground motion than the typical 500 to 2,500 year return period that we typically select with probabilistic. But there are other cases where the deterministic is the unconservative, because it has a return period of 50. Whereas if we were to perform a probabilistic seismic hazard analysis, we would select a more rare scenario. So in reality, neither of them is the worst case. It really depends on what we select. Okay. Are there any other like conceptual or arithmetic questions that you had from the first assignment? Yes, please. Epsilon is associated with the percentile. But it's not the value of the percentile itself. So actually, you can define your position in a normal distribution as the number of standard deviations you are away from the mean. So if you are at epsilon of 1, you are one standard deviation away from the mean towards the positive values. If you are an epsilon of minus 1, you are minus one standard deviation towards the negative values. Right? So if you now actually define the position, and for that position, you can find the equivalent percentile. So if you calculate the area of the curve until that value, that will be the percentile. So if you have an epsilon of 0, you are a right-hand term. And already we said it's a symmetric distribution. So an epsilon of 0 is the 50th percentile. An epsilon of 1, if you were to calculate 0.1 plus 2.1 plus 13.6 plus 34.1 times 2, you will have that an epsilon of 1 is about 84th percentile. And then an epsilon of 2 is the 98th percentile. Is this now clear? Okay. Any other question? Okay, so I think where we left last time was we were going over the PSHA software. Had anyone had the chance to run them on their computer to see if they work? Okay. So mm, so I have all the. I think these are software that I compiled maybe a few years ago. So I think it's still fine for Windows. But if it doesn't, then let me know so that I recompile them, or I can. You also have the access to the source code, and I can help you compile them yourself if your computer has, I don't know, any peculiarities. And I also added a file with like example files so that then you can also run them on your own. I believe last time we were. I think we finished the source file and we're going through the ground motion model. Is that correct? Fine. I think we were here. So, so we went already how we define the different faults that we want to evaluate the hazard, but we also need to define some information about the ground motion models to use and some information about our scenario of interest. So In this file, first we need to start with the name of the source file that we will be using in our analysis. And then typically either defined as a rectangle or more commonly as a distance, as a maximum distance. So you can assume you have, I don't know, your site here and you have like a fault here, a background zone here, and so on. As you go further and further away, there are more faults, but they tend to be, because it's unlikely that they will be the dominant scenario. So typically you define some type of like maximum distance that you use to limit the problem that you want to calculate. So this is R max. And it really varies. Like in seismic areas where you have a lot of faults nearby, you typically don't go beyond 300 kilometers. In areas where the seismicity is less, and so even things that are happening further away can have a noticeable effect, you typically can extend it to like 1,000 kilometers. After you do that, you define how many, here what is called number of problems is how many periods, from how many periods you want to run your analysis. So whether it's like a period of 0.1 seconds, 0.2 seconds, and so on. And for every period that you have, you repeat this block. So in this block, you define the period that you want to run. So this is for a spectral acceleration at 0.2 seconds. And then again, because we are going to do this numerically, we need to discretize and truncate everything. We cannot be integrating until infinity. So similarly, when we are going to run like if you remember, we had that the hazard we define hazard Z is the sum of n m mean times the integral of distance, the integral of magnitude, and the integral of epsilon. And then we had f of m, f of r, and f of epsilon. This now will go from -5 to 5, and as we saw from the normal distribution, already beyond plus and -3, most of the distribution, most of the mass of the distribution is within that limit. And next, we define all of the test Z values for which we are going to evaluate the hazard. So here we will define it for PSA of 0.01Z, a PSA of 0.03Z, and until 5Z. And then there is a spreadsheet that you can, like, for each ground motion model that you want to define, you can calculate, you can find the equivalent code. And so you say, I want to evaluate the hazard for 4 ground motion models, and the code for each of the 4 ground motion models that you want to calculate is this 4. And for now, you can leave this to the default values. This is mainly if you want to, like if you remember when we talked about the mixture model where we had the 2 normal distributions to better account for the hazard of the tails. So if that's a case that, if that's important for your site, then you can add the weights here, but most likely that's not going to be the case. So you can leave it to the default values. And then you repeat the same thing again, but this time for a period of 1 second. Is the structure somewhat clear? So after you do that, then you also, like if you remember when we looked at the deaggregation, that defined we had to define distance and magnitude and epsilon bins for which we evaluated the hazard, right? Because how did we define the deaggregation? We define the aggregation for some mu belonging to some magnitude bin, distance bin, and epsilon bin. This was simply like our hazard, so sigma and mean, but then the integration limits were from M2 to M1 to M2, R1 to R2, and epsilon1 to epsilon2 of all the distribution density function over the total hazard, nu for the same value of z. So in order to know which how 5.2, 5.2, 5.4, blah, 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 until 5.8.9. And same thing for the distances, like for R1 to R2 being 0 and 10, then 10 and 20, 20 and 30, until 1,000. And epsilons, it doesn't have to go until to minus 30 because we already capped it at minus 5. But let's say from minus 5 to minus 2, minus 2 to minus 1, and all of the different values. Then we also need to, so far we defined everything about the sources and the ground motion models. The last missing information is the information about the site. So we need to tell where our site is located. So this is like the latitude and the longitude coordinates of the site. The VS30, so the average shear wave velocity at the top 30 meters. And the values for z for the depth to 1 kilometer per second are 1.5 and 2.5 kilometers per second. So that was the z1, z1.5 and z2.5 that we defined. And last, the names for your output files that it will generate. So you will open the terminal on your computer, and if you're using Windows, you can use PowerShell, I would suggest. And then you can go to where you have saved the file. So in my case, it's documents, seismic hazard, and then I have this example. And what do I have? ls is to list the files. And then I have the hazard folder. And here, where is it? We have the fault file, so something similar to what we saw. If you open it, so it has 16 faults and then all the information about the faults. And then we also have the uh, ground motion file. So log. Okay. So again, the source file we use, the maximum distance, and here I was running it for 15 problems and all the ground motion models that we are using. And we also have the executable file code for the hazard. So if I copy Spotify. So we can start it. And so it asks if we are to how many analyses we are going to run. We only going to run one, so for that we enter 0. And then we have different options. Right? And option one is if you want to see how the integration of an individual model looks like. So in our case, we'll click option 0, and then we need to type the name of the file that we are going to use. So this is the ground motion file. So we are saying run one has dam 18 txt, and then it will go over it, calculate the total hazard. So this problem doesn't take too long. So I think it has 18 folds. So like now the budget. Once the code runs, it generates these output files. Most of them we have software to process them, but one file that can be useful to read even like as a user is the out3 file. So if you open that, and then also view. ETA, 0.05 seconds, 0.075 seconds, and so on. It gives us the hazard curves for all the scenarios, the total hazard, the Poisson probability that we saw how we can calculate from the total hazard, the mean magnitude, the mean distance, and the mean epsilon. So if you take all of this in Excel and copy them in Excel, and then why it didn't work? And in this case, it's delimited by space and tab. And you do that for this one, and then for all of these, finish, and then these ones. These last ones. Come on. No. Next finish. And last one, this one. Okay, and now you organize them so that they all start at the same location. First one, you have this one. So now, and we are missing the ground motion values. Plug this one. Then if we take this column as well, this row as well, and then say plot them as a scatter plot. And then we can convert them into log scale. This is our hazard curve. Hazard curves of the individual plots, as you did in homework 1, problem 3. And then you sum all of them, and you get the total hazard. So now if you know the return period that you get, you go horizontal on that, and then you find what is the ground motion value that corresponds to that return period. Any questions on that? And we also had at the bottom, if you see, the like for the return period that you care, you can also find the mean, magnitude, distance, and epsilon. So all of this, like you can use this now to select the appropriate time histories, right? We saw last time that if you know the magnitude, the distance, you can filter them and find what time histories correspond to your scenario. So this is the main software, but then there are some utility software to help you further pre-process the data. So one of them is UHS. So this will require file for UHS. So if you open this is much simpler in its structure. All the things that you need. So how did we define UHS? It's a uniform hazard spectrum. Is uniform in terms of what? Return period. So can you elaborate a little bit more? For all different. Exactly. So then to define that, we essentially defined in terms of its return period, right? So the first thing that we need to do is exactly that. Say how many return periods we have to define the UHS and what are these return periods are. So that's how we define the UHS. And then because again, we need to discretize the problem is how many structural periods we care to sort of discretize the entire shape. And those can be the same periods as before. So these 18 periods. And we need to order them in terms of like, this needs to be consistent with your, where did we have them? Like they need to be consistent with how you define them here. So like if you're going here PGA 0.05 and so on, you need to follow the same order when you define the UHS. Otherwise, it will get confused because it needs to go to know which block of data it needs to read. So you say like the first period that you define It's too tall for me. The first period that we define is the PGA. In this case, the out3 file that contains that period. Typically, all of the periods are in the same file. One of the reasons that this option exists here is because running the hazard for different periods can be done independently, so you can distribute it among many computers, and then you can simply combine the files only at the end. That's the only. But you do that, and then after that, you leave one line empty, and you repeat the same thing with the out4 file. The out4 file has all the data that it needs to do the deaggregation for you. So if we again take the program for UHS, go to the example and paste it here. From the terminal, we can go to that folder now and type UHS, and it is asking you for the file to run. So this is the input file for UHS. So it's run_uhs.txt. Run_uhs.txt. It runs, and then it generates this. I don't think I deleted it last time. So we said run uhs.txt. So it generates this output file. And where is it? Here. It gives us and if we take them and plot them, you can plot them in linear or log space. Then this. So these are our uniform hazard spectra for the, I think, 100 and 1000 year interval. Is it clear? And no. And then it will also give you the aggregation. So as we said before, like what is the contribution for the magnitude being 5 to 5.5 for distances between 0 and 3 kilometers, 5 to 0.55 for distances between 3 and 6 kilometers, and so on. So you can take this block and then so this is the aggregation in terms of I don't know which is columns and which is, but you can One axis is the distances and the other axis is the magnitude. And it tells you that the hazard is coming from those two bits primarily. So you can then, to save time, I will not do it here, but you can define the values for your axis. Um, yes. I think you are right. To have an epsilon, you have to have a, let's see. Um, so this is only in terms of here, epsilon being. Yes, you are correct. So this is the entire deaggregation, including all epsilons, and then you have the right? Uh, this is sorted, yes. So it's for like PGA, and then and also you need to define the hazard level. So this is the 200 here. Yeah, thank you for that. Any other questions? So then the last thing that you can also do is, I think as Chris mentioned, like we ran all of this, but what did we do here? We collapsed everything to the mean. So this is the mean total hazard here. It tells us nothing about how because the range can be this much, the range can be that much. And obviously, that's something that we want to know when we want to uh, when we are tasked with designing a structure, because depending on the uncertainty, we need to uh, properly, like, if we have a lot of uncertainty, then we typically want to be more conservative to make sure that we are not unlucky. And to get the sense of uncertainty, we can use the fractile code. So here, the files that we need are the the fractals. And then we need to define the input file for the fractals. Because doing this work analytically is very difficult. It tries to solve it through a Monte Carlo approach. So it will go and randomly sample branches of the logic tree to recreate the hazard. So that's why you need like the random seed and the number of samples. And the more samples you include, the more confident you are in the results. And then, as with the ground motion model, you define how many periods you want to use, and and the index, so like for the PGA, point 1, point 2, and so on. So, and it will give us the facts. We can also and we can also give we can also provide we can also define the hazard level. So we created the UHS here, but again, we can also create the UHSs for different fractals. And these are the return periods that you can use to define those UHSs for the different fractals. And if you go at the bottom, where do you define the fractal? How many? No, I think internally it defines the different fractal levels. So similarly, if we take this program and run it, then the first thing that you need to do is specify the input file name. So let's delete the output. So it's in this case is run fract txt, and what we will do is random sampling. And then you can open the output file that it generated. And so let's see. So this is for a period of, okay, these are all your ground motion values. So it goes from 0. So if you take them, shift them by 1. And let's say we only use the 0.1, the 10% fractile, because otherwise it will be overwhelming. The 25th, 50th, then 75th, and let's say 90 and 99th. 0.9. Okay, so these are all the fractals. In terms of mean uncertainty, this is 1% fractile, so only 1% of the scenario that we, like the ranges that we defined in terms of epistemic uncertainty are below this. Then we have at the middle the 50th percentile, and then at the top we have the 99th percentile. So in terms of all possible values that we chose for like the B value, for activity rate, for anything that judgment is required, 99% of those cases were less ground motion below that value. And then we can plot the mean on top of that. So this is not normally distributed. So you will see that the mean will start around the median, but then it will go to higher fractals or smaller hazard values. And the figure that we also had, as we said, also So it will provide this information for all the periods from the period of 0.05. Um, and then the UHS. So we have the fifth, 10, 50th, 90th, and 95th fractile for the hazard level that you define. Good things. No. Uh, something seems a little bit off. Everything is zeros for some reason. Why? There were zero in the beginning. Oh, there were. Okay, maybe the number of. I didn't realize that when I was running in the morning. So as I told you, like you go to get more and more accurate values if you increase the number of samples. But number of samples, then it will give you the uniform hazard spectrum. Forget about the plot. Doesn't make sense. But it will give you the uniform hazard spectrum, so as a function of the period for all the different. I think we are with time, so the other thing that I was planning to do is go over the homework. We didn't go over homework too, right? We will go over that on Wednesday. And on Wednesday also we'll have Professor Trinidad from Peru to show one of the projects that he performed, he's invited, so he will go over a project where he runs seismic hazard analysis. And so hopefully we can connect the theory that we have been covering with practice and how this is done in industry. I believe he will be presenting for a tailings dam. Okay, so on Wednesday we'll do that. The other thing on Wednesday again, please think how we can structure the class so that the time we spend actually matters. We are not wasting our time. And any suggestion will be highly appreciated. I think that's what I have for today.